All right.
So you can go to nice-challenge.com. No, it's not competition. It's a lab requirement. And then there's an email free to get started, so you send an email to them, or you can even fill out your information right here, and they'll get back to you. They're really good. And as long as you're educated, they'll set you up. Well, it says 4 years or 2 years. I don't know if you can make exceptions. So you can ask, say, hey, I have no students. I mean, it's just for education purposes. So, yeah. And we got really nice labs.
Okay. Well, anyway, let's start with the chapter 3 here. This is this material is the classic stuff that I associate only with CISSP. And I was pretty happy to learn this. This is the theoretical foundation of the security models we use. This is where, as far as I can tell, this is where CIA came from.
I'm sorry,
Yeah.
I can hardly hear you with the hum.
Yeah, I don't know. I don't have anything to do about that.
Okay.
Try moving up here. One thing you can do. I know. Anyway, so these security models we're going to talk about quite a bit, like Biba and Bell-LaPadula and such. Those are the fundamental intellectual models that led to the modern idea of cybersecurity. And then we'll talk about quite a bit more evaluation, accreditation systems, and a lot more. So there's a long, this one topic is enough for the whole day, probably. So here's the security models. There's a lot of them, and the big ones are Bell-LaPadula, Biba, and Clark-Wilson. Those were the big steps forward, and they approximately came along with confidentiality, integrity, and availability. As we discovered that there were 3 competing things in security. We came about largely through those models, but these other models are important too. And so here's the idea. You have up and down. You have low security level and a high security classification, like in the military, unclassified, confidential, secret, and top secret. So the issue is whether you can read up or write up, and whether you can read down or write down. So no read up is the original plan. The first idea of security, and the first security model, was that security is keeping secrets secret. The only thing they thought about was confidentiality, which is what most people think about. So if you want to keep something confidential, then you want to have no read up. People that are only allowed to read confidential information are not allowed to read secret or top secret information. So that is the security rule, no read up. You can only read things at your classification or below. That's what everybody imagines it is. And this is the Bell-LaPadula model. And that sounds simple and obvious, but if you're going to put it in a computer system, you have to formalize it and write code and rules that enforce it. And then what happened is this had unexpected consequences, which required security to get more nuanced, because this isn't enough to make a secure system. So writing up is okay, because you can take something and you can write to a higher level, because your only rule is you cannot read to a higher level. So a person with secret clearance can then discover something which is classified top secret, and then it can get classified above their level. So it is possible for information to flow up. And that doesn't violate confidentiality. But you have no write down. You are not allowed to take top secret information and copy it to a lower privilege machine, because that would expose it. So that's the plan. No write up, no write down, and no read up. Now, read down is of course allowed. People at top secret clearance are allowed to read secret and unclassified stuff. So that's the system. And that's what this does. So this is a state machine model, which is true of almost all the things we work with. Formally, mathematically, they are state machines. You have a system of users and files and computers in some state, and then you have transitions into another state. Like some user opens a file. Now you've moved from a situation where that user was not accessing a file to a state where that user is accessing the file. And what you have is a bunch of logical rules about which transitions from states are allowed and which transitions are not allowed. So you want to make a system where every possible state is secure, and there are no transitions that move you to a state that violates your security rules. Then you have what you call a secure system. So here's the Bell-LaPadula model developed for the military, and here's the rules: no read up and no write down. These are the simple security policies that would appear to be what you want to protect confidentiality. But the problem is it does not maintain integrity. Since you can write up information from a low privilege level can move up to a higher level and alter what's at a higher level. So what you get here is you get mission creep. And this is essentially what happened. There was a famous case where the KGB sent a team to break into a government safe and steal a document in Washington. And then they found out that another KGB team had already stolen the same document, but didn't tell them. Because this is the problem with confidentiality. Since everything is secret and everything is classified, nobody knows what they're doing. And they don't know what other people are doing, so people don't work together. That's the problem. You lose integrity. People wander off their mission because they don't have enough information to know what's going on. That's the problem. All right, so there's a tranquility property that says security labels don't change, and a weak property that says they don't change in a way that would break security. And then there's lattice-based controls. You can have, this is another system where you have subjects have roles and classifications and a least upper bound and a greatest lower bound of access. And you have this lattice with alpha, beta, and gamma and rules about who can reach each other this way. It's another attempt to formalize the transitions between the various states. So after the Bell-LaPadula model came out, and they discovered that it protected confidentiality, but it did not protect integrity. So what it is, it's over in one extreme of the CIA triad. They tried the Biba model, which is the complete opposite. No read down and no write up. Now this, I like to think, is like the Roman Catholic Church. You have a document at the top, the Bible, that can never be changed, and everybody can read it. That's what you have here. Nobody can write up. So the stuff at the top can never change, and the people at the top do not read anything lower, but people lower can read things higher. So this maintains integrity. You have one document at the highest privilege level that everybody can see and nobody can change. So everybody stays on target, but you don't have any secrets. This gives you integrity, but no confidentiality. So we now have mathematical models for the extreme security conditions in the corner of the triangle, which are not very realistic for real business, but they're mathematically useful to understand the concepts. So this gives you integrity, but not confidentiality. And so you certainly would not want this for a place with secrets like the military. But like I say, you might want it for places like a church where you have this holy book that everybody should know about, but it should never change. Yeah.
So say this one slow. So everybody at the top can read all the way down?
Not in this model. This model has no read down. In the other model, you have read down.
Okay.
In the Biba model. In the Bell-LaPadula model, you have no read down. So people at the top only look at the top. They can't read down.
So they can't read down.
That's right.
But the people at the bottom can read up.
That's right. And so this is the idea where people at the top know the secrets and they don't pollute their mind with this unreliable stuff from down below. And people down below strive to move up. Like Scientology works this way. You go through levels, and the Masons do. You go through levels and you learn the secrets, and now you don't bother with those, and you realize that all the lower levels are not really as good as the real secrets. So I mean, it's appropriate for things like religions, where it's not, where you don't have confidentiality, but you have integrity because you believe this sacred thing is perfect and shouldn't be changed. And I think the legal system is kind of like this, where we have precedents in the Constitution and the Bill of Rights that never change, and they're not secrets for that reason. Everybody's supposed to refer everything to them, and you have this percolating legal structure of people doing little cases in little regional courts, but it's only when they go right up to the top to get compared to the master document, like the Supreme Court, where you get the final word. So the Clark-Wilson is the, good, we got an online person, and I should try and mute him if I can get my system to cooperate. Escape, there we are. There we are, all right. And so, all right, so the Biba and the Bell-LaPadula model are useful as mathematical extractions, but they're far too extreme for real business. So the Clark-Wilson model gets you in the middle, like say Microsoft Active Directory domains, where now you're going to have some degree of confidentiality and some degree of integrity, both, instead of one extreme. Yeah. Yeah.
Biba model is the integrity extreme of the triangle.
Yes.
This model was which extreme?
I got it back. The Bell-LaPadula model gives you confidentiality but no integrity. That was the first model. They're alphabetical. That's how I remember them. Bell before Biba. So Bell came first because the first thing anyone thought about was confidentiality. And because of the Bell model, they realized this did not preserve integrity. So they made the other model, Biba, which preserved integrity, but this no longer had confidentiality. So now they had to improve and somehow get something in between. And that was Clark-Wilson, which continues to be alphabetical. So for at least these three, that's, yeah. Yes. Yeah, and we haven't talked about availability at all here. That's the third one. Very good, good. Anyway, I remember that's how I memorized them for my CISSP exam, is these are three that were big at that time. They've added a few more later, but those are still the main ones. And they were historical. They were about a decade apart, like 1970s, 80s, and 90s. So the Clark-Wilson model is appropriate for the real world. So you define subjects and objects, and you have these things called well-formed transactions and separation of duties. So you have constrained data items. Constrained data items are items that obey your security policy. And you have unconstrained data items, which are incoming data which may not obey your security policy. And so you have transactions, which will move data into your security structure. And then once you're in the structure, you make sure that all the allowed transactions do not violate security. And this is a more generalization of the previous thing where you would have no read up, which would violate confidentiality. Yeah.
Could you give us an example? A UDI is data that doesn't require integrity.
Yeah,
So
like untrusted.
It would be a vendor from outside.
Right, like users are typing their name and address into a form. So it comes in as an unconstrained item, and then you want to turn it into a constrained data item, so it's recorded in your system, and now you have to preserve it. It's got a hash value or something.
So it's like create an account.
Yes, like when you create an account. And so people type in stuff, and then you go through some process of deciding whether it is acceptable, whether they're eligible, whether they made a typographic error or something, and then you create a constrained data item, which is something you now protect, because you now made sure to obey your rules. So separation of duty, we talked about this before. One department collects money, another issues payments. Neither of them is allowed to initiate purchase orders. This sort of thing is done to avoid one person having the power to abuse finances. And there's it's not in this list, but there is a special transaction which takes the UDIs and turns them into CDIs. I forget the name for it. But there's a special, which is a sanitization process. Like you type data into a form, and then it goes through some checks, like make sure the zip code has the right number of digits. And so you have untrusted input, and the special sanitization process turns it into trusted input. And that's part of this model. Anyway, so I got a few cahoots about that stuff, and then we got some more models. My cahoots are here. And I can get rid of this. And I think I now have sound and everything. In fact, I do, because I heard a bing bong when people joined. And my cahoots should be in the favorites. And this should be 4A. Okay. Because when I wrote these, it was chapter 4 in that book, but it's chapter 3 in your book. Anyway. Oh, I might as well put up the glorious scores. So I put the scores in a spreadsheet. And so we can keep track of it by chapter. So those are the scores so far, and I'll have it each chapter here. Yeah, 4, 5, 4, 9, 8. Yeah. Yeah. Anyway. All right. So I guess I'll. Are more people joining? No screams of protest? All right, I'll give it another 5. Oh, here's 5. Okay, I'll give it another few seconds to see if we can get up to 6 anyway. We got Kahoot abstainers. Well, here we go. Okay. 5 more seconds. Okay. So which one gives you confidentiality but not integrity? That's Bell. That was the first thing. The first thing people thought of was confidentiality. All right. Which one uses alpha, beta, gamma? That's the Lattice model. And this is kind of the superficial way to handle CISSP. You don't know much about it except a few words about it. That's what they mean, a mile wide and an inch deep. All right. Which one enforces no read up? That's Bell, the first one. No read up is confidentiality. The secret people can't read the top secret stuff. All right, which one has no read down? That's the other one, Biba. All right. So, Robert, Jane, and FDSGZ. All right, Robert is 3, Jane is 3, and I have a new name, FDZZ, okay? Is 3, all right, good. So, all right, so then there's an information flow model that focuses on how information moves from one level to another. And that's this system where you talk about writing up and reading down. Then there's also a Chinese wall model. You hear about this in legal companies. Like a large legal firm might take a case, and then they might take another case that overlaps with that case, and now they will have to have what they call a Chinese wall, where the lawyers on one team will not talk about this to the lawyers on the other team because there might be a conflict of interest. So that's an issue. And they had a system here for consultants in banks. It's the same issue. There are rules, administrative rules, I think, to try to handle this situation. All right, non-interference is a desirable property of a security system where data at one level of classification does not affect data at another level of classification. This turns out to be very, very difficult to achieve in practice. So if this fails, then there is a covert channel. There is some way to discover data that you're not allowed to see indirectly. One of the common side channel encryption is one area where this is a huge problem. If you have strong encryption routines, they almost always leak information through side channels. For example, if you look at the power consumed or the radio emitted by a computer dial encryption, that leaks out information about the key. And if you measure how long it takes to encrypt something, that often leaks out information about the key. There's another one I know, I've heard about this, spies that want to know when the US is going to perform a military action, look at the number of pizza orders at night in Washington near the Pentagon, because they make their staff stay late and they all order pizza. So when a lot of pizzas are ordered, that means a major military thing is underway. And that is an example of information leaking through a side channel. And that turns out to be extremely difficult to prevent. All right, then there's the take grant model. Yeah. Yeah. Mm-hmm.
So, so a cryptographic key. So, do you know which kind of are they using, say, SHA-1 compared to some other, because of the time it takes, or the power it consumes, or both?
Both of them leak it. The main example is not hashing like SHA-1, but encryption with, say, RSA. That's what's been tested extensively. And there are many ways to break RSA encryption with side channel attacks. One way is to measure the time it takes. One way is to measure the radio or the power. And one very interesting way is to look for errors in the computation. There was a test where they lowered the power supply to make a processor make more errors. It turns out if you take the OpenSSH library, computing RSA encryption, and it makes 1 bit error during the computation, that has a non-random result, non-random effect on the result. So by encrypting the same thing 1,000 times and having 100 of them that made errors, they were able to completely crack a 1024-bit key. And this, now they did that by lowering the power supply to increase the number of errors, but even real computers have errors of a certain level. Even with error correcting RAM, they have errors. And now when the amount of RAM in computers went up to like 1 or 2 gigabytes, they calculated that now cosmic rays passing through the Earth are frequent enough that computers will now have an error like every day caused by a bit flipped by a cosmic ray. So it is absolutely the case that computers are not 100% perfect. And so if you can just make it do the same calculation for a couple of days over and over and over, some of them will have an error. And those errors are not random. And you can deduce the key from the error. And that's one of many techniques. It turns out that there are many, many of these techniques. And we'll later talk about the padding oracle attack. This is why people get very afraid of cryptography. Cryptography is beautiful mathematically, but it has a certain structure. Like you have a secret here, you encrypt it, you send it over here, and the attacker can only see the ciphertext. And the problem is, in the real world, it's not true that they can only see the ciphertext. There are other things they could measure, like the timing. And there's another one, for example, if people want to geolocate people. The one technique is you take their IP address and you find out which their internet service provider is, but that only gets you to like the right town. UC Berkeley did this a couple of years ago. They could geolocate people within like 100 yards just by measuring the time it took for a ping to go there and back, because they would just measure the time in the cable and the speed of light and from like 3 points. And they were able to locate people precisely with that. And that's another thing people don't think about. And here's another one for like software pirates. The RIAA would really like to know who downloaded a movie. But they don't have your MAC address. All they have is your IP address. And your IP address doesn't really say who you are. It just says where you are. If you're in a coffee house and somebody else comes in, they might get the same IP address. So another thing they did was they checked, if you look at the traffic coming from a machine and you look at the microsecond level or nanoseconds, machines have a different delay between the bits. They're not perfectly the bits are not perfectly timed. There is an error, and that error depends on their hardware, and they were able to fingerprint machines and identify them, like pick one machine out of 100 with a high degree of accuracy just based on the little defects in its network transmission, the same way you might take a bullet from a gun and look at little scratches on the edge and get a sort of fingerprint. So this is the problem. In the real world, there are side channels that give you information that is not in the mathematical model. And that's the problem. The math can be beautiful, but whenever you really build something, there are weak spots that were not considered in the math. This got me when I was in grad school. I was a theoretical physicist. I worked in an experimental lab, but I was mostly doing theory. And there was another guy in our lab who was the grease monkey that built all the equipment, and he graduated and left, and I was now the senior member of the group, and I couldn't fix the equipment. And so one day I was trying to tune up the laser, and I had to shoot it like 100 times, and a whole capacitor bank exploded. And people said, "You idiot, you have to let it cool off between shots." And I said, "No, you don't, because capacitors have a 90-degree phase relationship between the current and the voltage, so they don't generate any power." And they said, "Yeah, but those capacitors aren't perfect. They leak." And I said, "Oh, I never thought of that, because I only knew the theory." And in the real world, there are problems that are not in your simple theory. And that gets people. Anyway, so then there's take grant, where you do the rules where you take permission and grant someone else permission, create permission and remove them. And then you have rules of how these things are done. So Alice can create and remove privileges to these secret documents. She can grant Bob permission to read them, and so on. And Bob can take Alice's privilege because he's higher in the management structure, so he's allowed to remove her rights. And that you have a system where these are the transactions, and then you have rules about who can do what. So you have an access control. Yeah. Yeah.
CR stand for?
I don't know. I think create and revoke or something like that. Is it good?
G's grant.
Yeah.
So
Yeah, I'm not sure. It's a good point. I don't know what CNR are.
Yeah.
Yeah.
So, yeah. Okay. Bob can take.
Oh, create and remove privileges, right? Alice can create and remove privileges, right? So.
Alice can grant.
In fact, this reminds me of the very low security model discretionary access control, which is what a home PC has. Home PCs, they call it discretionary access control. You own the PC and you can grant privileges. You can share the file with anybody at your discretion. And so Alice, this might be her personal folder, and she can just decide to give someone permission to get in there or remove that permission. And that's, of course, a low security model because the end user can just give everyone full control. In a higher security model, only the higher privileged person would have the right to change permissions. And that's the mandatory security model. In the Security Plus level, they have just 3 categories. There's discretionary access control, and mandatory access control, and then there's other ones like rule-based access control. And the discretionary access control is where you have an owner of an object and they can do anything they want with it. And the mandatory access control is where there are executives that have to make all those decisions. You have to apply for permission to be changed, and it has to be done by a higher authority, like in the military. So you have a matrix here, an access control matrix, something like this. This is what you'll see if you go to, say, a Microsoft Windows machine and look at the properties of a folder. You have usernames and then whether they're allowed to read, write, and execute on those folders. And a matrix like this is implemented by the system. And there's other ones, like here's a Zachman framework where you have this what, here, where, who, when, and why, and then you have various roles of people. This is what's generally done, of course, in Active Directory domains and at companies. You do role-based access control, where you do not give individual people permissions. You sort the people into categories, and then you give the role a permission. So the builders can do one thing, and the programmers can do one thing, and the users and owners and planners, these different categories of people can do different things. And then you move people through these roles. This is usually the best way to do it. And the general rule is to have a small number of roles and make it simple. It's very easy to create a snarled mess where you lose control with this kind of work. So there's the Graham-Denning model where you have subjects, objects, and rules, and then you have rules like this: transfer access, grant access, delete access. You may, in the Linux operating system, all you have is read, write, and execute. In Windows, you have actually 14 fundamental permissions, and they're grouped into 6 things like full control, read, write, execute, list folder contents, and so on. The fundamental, and that's what happens in operating system design and security system design. You define what the fundamental permissions are, and then you assign them to groups of people. And that's the kind of mathematical and computer science planning that goes into developing these models.
So this is would be a hybrid of role-based and discretionary role models?
Well, you could create a discretionary access control model of this or a mandatory access control model of this, because the difference is who makes the decision. So it could be used in either situation, I think. Here's another one which treats subjects and objects the same and therefore only has 6 operations: create object, create subject, destroy subject, create, destroy, enter, and delete rights. And then you can have modes of operation. This is why, I don't know if this is still true, but I was told by some of my students years ago that there were people in the Pentagon that had 7 computers on their desk because they had to have an air gap between all the security levels. And then people said we'd save a lot of money if we just used virtual machines, but then it wouldn't really be as strong a security boundary, because leaking from one virtual machine to another on the same processor, of course, is easier than crossing an air gap. And so you have to decide what to do. But here's the modes of operation, and that's the issue here. So you can have a dedicated mode, and that's what I'm talking about. This is where you have a separate computer, a separate system for each level of security with an air gap. So that's the simplest and probably most secure model, but it's also the most expensive and clumsy. So everybody who has access approval and need to know if they're on that system. So anybody who can get to that system is allowed to use that system, and nobody else can use it at all. So you have a dedicated computer, and only the top secret people can use the top secret computer. That system is dedicated just for that category of information. Then you have system high, where you can mix information on there, but everybody has to be cleared for the highest level of the information on that machine. So it may contain lower level information, but you don't let anybody on it unless they are cleared for all the data on that machine. But then there's compartmented. This is where you are trying to save money, So you have one machine that has different levels of information, and objects are placed in compartments, and people are somehow approved for a certain part of the information, but not the rest of the information. So now you're trusting the operating system to enforce that. This is what you have in, say, Windows domain. You have many users all connecting to it. They're not all allowed to do everything, and it's deciding this user is the administrator and they can do that. This user is not the administrator, so they can't do that. And then there's multi-level, where you have objects with different sensitivity labels and people of different sensitivity labels all coming into the same machine, and your operating system is supposed to be trustworthy enough to sort that out. This is what's really done in businesses, but as we know, it's pretty risky. The most common security flaw I know, well, one of the most common ones is local privilege escalation. Every 3 months or so, there comes exploit leaks out, so you can escalate yourself to root on Linux systems, and there seem to be a ton of them on Windows that they never fix. If you use Metasploit, you can escalate yourself to system almost all the time. So the idea that one user can't read another user's files on a Windows machine is a very weak security boundary. It is a quite elementary hacking exercise to escalate yourself to administrator and move across on the same machine. So that's why this is kind of problematic, but of course, it might be the cost-effective option if your security needs are not really that high, and that's the issue. Anyway, that's a multi-level system. All right, so then you might have evaluation methods to rate how well you've accomplished these things, and the main one is TCSEC. It's the one you always hear about. This was the orange book from the DoD in the 80s. This was defined these security levels and defined a whole bunch of terms that became the standards in computing for a long time after this. There are other ones that came up later, ITSEC and Common Criteria, but it all started with TCSEC, the orange book. There was a rainbow series of colored books from the military, and this was the one for IT, Trusted Computer System. So it defined, it said if you're going to handle government or military data, it must be on a trusted computer system, and the rules in this book explain what is a trusted computer system. This is how you ended up with a Microsoft Windows Vista, and later your motherboard has to have a trusted platform module to hold the cryptographic keys, and that is from this book. The trusted platform is the computer system which meets these requirements, so you can now trust it with data. And so they added a special chip to be the trusted platform model to make a Windows machine a trusted platform, which means the military can use it. It all comes along this way. So it gives you these levels from A to D. So D is a machine with essentially no protection at all. C is where you have discretionary access control. So this is like I talked about before. You have owners of objects, and the owner can decide at their discretion who else can see it. This is what normal home PCs are like. Then you have mandatory protection, like B. This is like a Windows domain, where there is like a domain controller and a domain administrator, and you can't just decide to share an object. You have to go up to the domain, and there are different levels here. And then you have verified protection. This is the highest level, and this is where you have management that is not only enforcing rules, but they are auditing to see how well the rules are being handled, and they're constantly improving the system with a loop to make sure that your violations are fixed and problems are fixed and all that jazz. And of course, A is the best and the most expensive and the most difficult to achieve. And now you have these levels, and now you can say this data can be on a C, but it can't be on a D, but this data must be on an A. And that's the point. Now you rate machines. So there's the red book, which was the network version of this. And ITSEC was the European analog, came out later essentially to do the same thing. It had functionality, assurance rules, and effectiveness and correctness levels. So you'd have E0 was inadequate, and E6 was the formal model where you have this whole closed loop of constant improvement, and they have ratings in between that are quite similar. So here's a match between the TCSEC and the ITSEC, and approximately they just map one to the other, but there are some little details. And all right, then there was an international criteria, because of course these were defined by individual nations. So for the this is intended to replace TCSEC and ITSEC. So now you have target of evaluation and security target. And this, I think, is easy to understand. Like I mentioned in the last lecture, the US military has defined what they should be doing for security. but then they have audits, and they found for years they're like 90% out of compliance. So you have what you're trying to do, and then you have what you really have achieved. So there's a protection profile for a specific object and an evaluation assurance level, which is the score of the tested product. So now you have a system whereby you can rate security. Here we reach, I should mention, this is a dirty little secret of this industry. There are no security metrics that are worth anything. This is not a science. This is an art. People would like to say, every vendor would like to say, you're likely to get hacked, but if you buy our product, that likelihood will go down by half and you will save $10 million a year because you won't get hacked anymore. And we like to say your security is now a 6, but if you buy our product, it will go up to a 7 and that will save you this much money. That would be a science, and we are not there at all. There is no way to rate people or firewalls or operating systems or anything with a number that means anything. Nobody knows. There are many, many attempts to do it. This is the first attempt to do it. Another thing people like to do is count how many vulnerability reports there are per year in a product and decide if they're good or bad based on that. So the Linux people used to say we're more secure because Windows had more security bulletins per year than we did. But then people said they aren't all the same, so they tried to rate them by how secure they are. And then a test came out from Rapid7 a couple of years ago. Rapid7 scans the entire internet for vulnerabilities, and they find who's infected every hour. And they do this in partnership with the Department of Homeland Security, even though it is completely illegal to do so. And I was interested because you cannot scan someone else's computer for security problems without authorization, according to the law. And I read Marshall Hoffman's explanation of this because I've done things like this too, and I wondered how to do it. He wrote a document saying, we are aware that this is breaking the law, but we have decided by publishing the results and making it clear to everybody that we're a beneficial, helpful organization, hopefully nobody will punish us. And that has in fact worked so far. So anyway, from this, they know what attacks are working, and they found that like 90% of all attacks use vulnerabilities that are like been patched 5 years before. So you could argue that you're totally wasting your time putting on the latest patches and updates and having the best trained staff. But in fact, like something we saw yesterday, if you just did basic, simple hygiene, that would probably be your most effective thing. People get hacked because they do something stupid. Not because they didn't have the latest fancy, flashy gadget, but because they just left a default password on a system, or no password at all, or something utterly foolish, or attached some unauthorized device, like an IoT device that has a known vulnerability to the system. Very simple problems. Left the door open so they can go outside and smoke. You know, people, anyway. But that's why I just mentioned, you could argue that everything you're learning is garbage. There's not a science here where we know that training people will save this much money. We just sort of feel like knowing more and training people has got to be good, but the evidence is not really there. The reality is everybody gets hacked anyway. But this is one attempt to move it, to make it more scientific, quantify things. The military has to have some rules, so these are the rules. People argue like mad that these rules and things like the CISSP certification are very useless because they really don't mean that someone with that certificate really knows more or they're really going to stop more attacks or anything. It should be that way, but it's not really that scientific yet. So here's the common criteria levels. And again, you've got functionally tested just means it works at all. Then methodically tested and checked. Then you get down to a formal, verified, designed and tested. This is moving through the levels of just having a bare product to have a product that has a bunch of documents and management levels proving that many things have been done to consider the security problems and address them. All right, so I got some cahoots about that stuff. For A2, should be somewhere on my list here. There we are. Kahoot punishes me for not having paid by not sorting things. Anyway. It's a very good service. I might even pay for it someday, but so far they haven't made me pay for it. All right. I think 7 is the maximum possible. I think one person left the room. 6 is the maximum possible. I'll just carry on. All right. Okay. What security feature prevents a covert channel? That's non-interference. Your high security activities do not cause any change in any low security features of the system. That would be great. It's very hard to actually achieve, but that is what you really would like to have. So which operation mode enforces an air gap? That's dedicated model. You have the dedicated machine for top secret, another different dedicated machine for secret, and so on. Very simple and really quite secure if you can endure all the annoyance and inconvenience caused by it. Which one uses a reference monitor to control access? Okay, that's the multi-level system. We have different levels of users and different levels of objects, and your operating system is supposedly trusted enough to untangle it all and not let the wrong people see the wrong things. All right, so what TCSEC level do you have if you just buy an ordinary home laptop? That's the lowest. What's C? I thought it was the lowest level D.
D, that's right.
I thought it was D, but well, I might have made a mistake. Let's go back and look, because I expected a D. Let's see. TCSEC. Okay, here we are. Okay. Oh, it has discretionary access control. That's right. If you buy an MS-DOS laptop, you have D because it didn't even have, it had fat file system, so you couldn't even like have administrators have full control, but users can only read. You couldn't even do that. That would be D. C means you do at least, you can separate, you have different users and different users have different rights. That's right. Good. Okay. Good. All right. All right. So what's the modern international evaluation model? That's the common criteria, is the modern international model. All right, good. So I've got Jane for 3 and FDZ. Look.
I have 4, so 7.
Robert. You get 3 points each time. Yeah.
Oh,
Yeah.
I get 3 points.
Yeah, each time you win, you get 3 points. Good.
Oh,
Are you Jane?
yeah.
Good, okay. Well, you're number 2, and you're B, right?
Yeah, no, I'm Robert.
Okay, B is,
Over here.
oh, B left.
That's the Robert.
Anyway, you're missing out. All right. Well, fair enough. Let's see. Oh, my power is not charging. What's wrong here? Right. Oh, there's that one. Oh, it's not plugged in. Well, that'll do it. Okay. A layer 1 problem. Okay. All right. So, all right, we started at 9, it's 9:44, so we will continue. All right, so here's some design concepts. One issue is layering. This is a big issue. You know, back in the days of like a Commodore 64, you would buy a word processor and you'd print to one printer. And if you buy a new printer, you'd have to get a different word processor that knows about that printer. And this, of course, is a drag. So they separated function into different layers. So you have a printer driver that comes to the printer, and now your word processor can use any printer as long as it comes to the right driver. And that leads to these multiple layers. So you have hardware, the kernel is the heart of the operating system that connects to the hardware, like the drivers. And then you have the operating system above it, which lets you log in and have permissions and stuff. And then you have applications on top of that. And now you can buy something like Microsoft Word and you can install it on various different operating systems, and they can be connected to different hardware with different drivers, and it will work on all of them as long as everything is obeying all the rules, which of course is not always perfect, but mostly this works. So layering is a big issue. Then there's abstraction, where you don't bother users with what they don't need to know. So you just see like a a link to double click to open a web page, and you are not aware of the HTML and the TCP and the Ethernet and everything that's going on to make that happen. You just see the results. So you only see an abstract representation of all the internal complexity. And that makes it possible to focus on just one level without worrying about the other levels, as long as everything works. Then you got security domains. So you group things together. One simple group in computing systems is you have kernel mode and user mode. There are actually 4 protection rings in computer hardware, but all modern operating systems only use 2 of them, 0 and 3. Kernel mode is the microprocessors have a set of instructions, and only processes in kernel mode can use them all. There are certain instructions that you are not allowed to use in user mode. And basically, kernel mode is where you're allowed to directly touch the hardware. So if you want to send a 5-volt signal out the network card, you can't. There's no program you can write in Visual Studio or whatever you're using that can do that. All you can do is ask the kernel driver to please send a packet out the wire. And for example, if you are using Windows 7 or Windows 10 and you would like to change the TCP timeout, this is something I did in my project. So for my classes, I have students do a manual TCP handshake where they send a SYN, they get a SYN ACK, they have to look at the packet and find the sequence and acknowledgement numbers and change them to make the ACK. The problem is that takes them some time, and Windows will time out in about 40 seconds and they don't have enough time to do it. And in Windows 2000, you could change the TCP timeout, but Microsoft didn't like that. So in modern versions of Windows, you cannot change it. There is no adjustment available to you. You can't send one packet out the network adapter. All you can do is ask the network adapter to please make a connection, and it will send all the packets and adjust the timing, and you have no control of the details of that. They have not given you that privilege. This is why, hacking tools mostly run on Linux, because ever since Windows 2000, you don't have raw sockets on Windows. You cannot control what goes out the network card. You're stuck with whatever Microsoft wants to let you do, because they really aren't trying to make a hacking machine. They're trying to make a normal user's functional machine, and they don't want to give you direct control of the hardware, and you don't have it. Only the kernel has hardware. So if you're in user mode, where we spend everything on the desktop, everything you launch with the mouse, everything you do after you've logged in is in user land, you don't have the ability to directly touch the hardware. All you can do is ask the hardware drivers to do whatever options they give you. And if you want to do something that the hardware drivers don't give you, you can't do it. This is why if you go to DEF CON, there's a bunch of vendors, and at first you might be surprised because the vendors are selling old used junk. It looks like a flea market because you can't buy the newest fancy network card at DEF CON. Nobody wants it. They want specific models of old used Wi-Fi cards for which there are hacked drivers that give you full control of the hardware so you can hack into networks. And people find them and they reverse engineer the drivers, and there are only certain ones that can do it. So if you want to hack into wireless networks, you have to either pay a lot of money for an expensive specialized hardware that runs on Windows, or you have to find specific old hardware that have been hacked and get the hack drivers that run it, so you can, from your user land, control and send out things like false packets in the wireless card that pretend to be from a different user, which you have to do to hack into networks. And of course, the normal Windows system do not have that option, because that's not something any normal person should be doing. And Microsoft is not trying to give you a 100% control of the machine. They're just trying to give you a machine which normal people can use to do normal things. Anyway, so, all right, it's kernel mode and user mode. So here's the ring model. There are 4 models in the hardware. Ring 0 is the kernel. Ring 3 is user. There are 2 models in between, and there have been a few operating systems that actually enforced them, but they didn't succeed, and all the modern operating systems use only 0 and 3. Well, you could give them names, but actually one thing that has happened is they now have virtualization and hardware-assisted virtualization, which is like another ring beyond these. But I mean, you could call this kernel mode, you could call this like high security system mode, low security mode, or something. I don't know if they ever had names for them. The operating system, the hardware has the ability, but the operating system would then assign a name and a function to it. And this didn't turn out to be as valuable as people thought it would be. So, and hypervisor mode is what they call ring -1. Because now you have this thing called hardware-assisted virtualization, where your hardware knows you are a virtual machine and somehow assists that to happen. That's why if you want to run something like VMware Workstation, you have to have a modern laptop. You can't have one that's like 10 or 12 years old because it doesn't have hardware-assisted virtualization, and modern versions of VMware will not run without it. So your hardware has to know you're planning to run a virtual machine, and so they now call that ring -1. This allows virtual machines to access ring 0 and directly connect to the hardware. Without this, all your virtual machines will run slower and buggier because they're running in user land, and they're having to go through drivers that are not really the same operating system as the operating system they're simulating. So they have to like translate your, if you run a virtual Linux machine, they have to translate the system calls into, say, Windows calls. It doesn't really make a lot of sense. So this is Intel VT and AMD V, and there's other ones out there. The hardware-assisted virtualization, which adds another level of complexity to this.
Yes. Go back. So only two are used. Sorry. Go back to
Yeah.
three. Only two are used by Linux and Windows.
Yeah, only
Which
0
is 0 and 3.
only 0 and 3. Yeah, the ones in between didn't turn out to be useful, and the operating system did not employ them. All right. So another big category is open and closed systems. There are open systems like the IBM PC published the hardware specs so everybody could build one. This turned out to be a questionable business decision. IBM never made any money from the PC. They had a huge bureaucracy. They said at IBM it would take us 6 months to ship an empty box because we would spend 6 months deciding who the manager was, what the branding is, what the discount is, what the channels will be. And so average people in like a garage would just start building cheap PCs and selling them. And so the stuff you could get from like amateurs was more modern and valuable and cheaper than the stuff IBM was shipping, and they could not win. So they never made any money out of the PC because it was an open system. The Mac was closed. The early Macs had no serial numbers on the chips. You weren't allowed to change anything. They didn't publish anything about it. You were totally not allowed to build your own Mac, and they made it as impossible as they could, and they made a pile of money because the only way to get an Apple II was to buy an Apple II. You could not build your own Apple II. And so that's a closed system. All right. Then there's hardware architecture. So you got a system unit. That's the main case here that has the motherboard and the RAM and such in it. The motherboard is the main chip in there that has the primary hardware. This is the A+ part, of course. So you've got the bus is the communication line between chips. So you've got the central processing unit, the RAM, and the hard disk, and then you have a bus moving data to the display and the keyboard and mouse and all that. There's the Northbridge and the Southbridge in modern computers. The Northbridge is for really fast communication with things like RAM and video memory, and the Southbridge is for slower communication with things like the hard drive and the keyboard that really don't need the fastest response. And so the CPU does all the processing on the machine. The arithmetic logic unit does everything that involves flipping bits and calculating things from the bits. And the control unit determines which instruction you're processing and which one should come next. So the control unit is sort of like the secretary taking calls and transferring them, and the ALU is the one that actually does the work. So there are 4 steps to this instruction. You fetch the instruction from RAM, so you know what you're supposed to do, then you decode it and execute it, and then you put the result somewhere. It might go into register, it might go into RAM, and then you go through this loop. So most instructions take several clock cycles to process. So if you say your machine has 3 gigahertz, it's doing 3 billion clock cycles per second, but a typical instruction will take maybe 6 clock cycles, and each instruction takes a different amount of clock cycles. Interrupts are urgent signals that happen in the system. Something might happen, like the user presses a key. Now the operating system should stop whatever it's doing and listen to that because something should happen, like launch a program, so it'll launch an interrupt. And the CPU is told to stop its current task, save where you left off, like you would do if you're working on something and the phone rings. You somehow make a record of what you're doing, go take care of this other job, and then come back and try to pick up where you left off. This is how you hack into machines. In my exploit development class, this is what you do. This process of returning from another task back to resume where you left off is the most vulnerable step. This is how buffer overflows work. You change the return pointer so that when you think you're returning back to the original task, you're in fact doing something else. That's how you take over machines most commonly. Anyway, this is, so in modern, in the old days, when we used to use MS-DOS, I remember I would work on a document, and when I printed it, it was time to go get a cup of coffee, because while it was printing, you could not do anything else. It was a single task machine. You'd run Word and write the document. Then if you had to make a graph, you'd run like a graphing program and make that document. You would print it, and you couldn't do anything until the print job was done. And then you'd print the other thing, and then you would take tape and tape the document, the graph on the page, because your graphing program could not interact with the printing, with the word processor. That's the way it was. That was a single processor machine. This, of course, was no fun. So we got multiprocessors now. You can launch multiple programs and run them at the same time, and you even have multiple threading. This is because there's a huge problem in computing at all levels, which is there are fast processes and slow processes. And what you don't want is your fast CPU to be waiting for something slow, like the hard drive or the network card, and doing nothing while it's waiting an eternity for the next packet to come in on the network card, which might take milliseconds, and it's a gigahertz machine. It could be doing a lot of work, so you have threads. And the idea is you break the job up into different subjobs that can each proceed independently, so even if one of them is waiting for something, the other threads can move forward. So that's multitasking and multiprocessing. Multitasking is what I described, where you can open several windows and have several programs open at once, and the processor will do a few cycles for this one, a few cycles for that one, a few cycles for that one. Multiprocessing is when you have multiple processors. Like modern machines typically have 4 cores or more. There really are 4 processors in there, so it can actually be doing 4 things at once. Multitasking means you only have one processor and it's strobing from one process to the next. Multiprocessing means it actually has multiple processors. All right. You can have a Watchdog Timer, which notices if the machine is freezing for too long, and then it reboots. Cisco routers especially have this. There's a thing called check heaps that walks the heap every 30 seconds, and if the heap is corrupt, it just reboots the router. This makes it difficult to hack into Cisco routers. Cisco routers are an interesting operating system because they have no error handling at all. If you execute a divide by 0 on a Cisco router, it reboots the whole machine. It makes no attempt to pop up a message or tell you anything, because the use case of a Cisco router is you put it in the closet and you use it for years, and nobody here has any idea how to use it at all. So you don't want it to pop up a box and expect attention or anything. You just want it to reboot and move the next packet. And it's okay if it loses some of them. It's just supposed to stay up most of the time. So any error at all, it just reboots the machine. And that way it accomplishes its job. CISC is the old Intel model. This is where you have a lot of machine language instructions. There were like 10,000 machine language instructions in the Intel Pentium 4, and I think even more later, with many, many instructions. They're all about the same. There's like add. You can add register to register. You can add register to immediate. You can add register to memory. You can add register to indirect memory with a register telling you what the indirect pointer is. And then you can take the result and put it in memory, put it in the register, put it in a indirect address in register, many, many variations of move and add. But all these complicated options, the idea was you would have code that was efficient because the processor designer found the most efficient way to do all these things. And now when you compile your program, it will let the hardware do the work. What happened, though, is nobody could keep up with the complexity, and real compilers didn't use hardly any of those instructions at all. Like less than 10% of the instructions were actually used by any code. So you're kind of wasting your time designing them all in. So the alternative was RISC computers, where you reduce the instruction set and you have a small number of simple instructions in the processor, and it therefore takes more individual instructions to process the program. This is what ARM has got, and what I've read in the industry magazines is ARM 1. People are abandoning Intel and moving to ARM. They say soon our desktop machines and our servers are all going to run on ARM. ARM is, I don't know if it stands for anything, but it's an alternative to Intel. Advanced RISC machine?
Yeah.
Oh, great, thanks, good. Anyway, ARM is what's used in cell phones and in Raspberry Pis, and increasingly, and soon I've heard announcements that very soon we're going to have ARM laptops and ARM servers, because apparently it gets more processing done with less power. And power and heat dissipation is turning out to be the real limit. So I teach people how to hack x86 machine code and now x64, and both of those are on the way out, focusing on current trends, although it's going to be a gradual transition.
I believe at one point the
Apple used Motorola,
Okay.
and that was not ARM, but it was a similar. So Apple used reduced instruction set, then they moved to Intel, and now they're moving on. I think they've announced that the next Mac will be ARM. I'm not sure. I saw some news about that. So everyone's moving to ARM. ARM is very interesting machine instructions. When you look at ARM assembly, one thing that's weird about ARM is everything only works at registers. You have 16 registers, and if you want to add something, you can only add register to register. So if you want to add one memory location to another, it takes 4 instructions or 5. You have to load this memory into a register, load this memory into a register, add them into a register, take the result and put it back in memory. It takes like 4 instructions to do what one Intel instruction would do. Add this to that and put it there. And that's the point. It has a simple instruction set, and you have to use more elementary commands to get the job done. Of course, they all can do the same thing, but that's what's winning. So then there's direct and indirect addressing. You can add EAX8. This is x32 assembly language. So to add 8 to EAX, your EAX will go from 1 to 9. If you add bracket 8 to EAX, then it goes and finds the contents of memory location 8 and puts that in EAX. That's indirect addressing. And here you add 8 to the thing pointed to by EAX. So EAX has 12, so you go to location 12 and you add it there. The contents of a register or memory location can be an immediate value or it can be an address. Now, this is why all the hacking works. Unfortunately, computers do not know what they're doing. They just have a pattern of bytes. They don't know if those bytes are a music file or a text document or machine language instruction or addresses. And so almost all hacking involves inputting something that is supposed to be treated as data, like network or a username or a password, and then tricking the computer into interpreting it as instructions. Because the same bytes could be interpreted as instructions or data. There's no difference. One thing that has occurred to me frequently is if you'd asked me, I would have said make every byte 12 bits, 8 bits of data, and 4 bits to specify the purpose of the data. And if you had done that, almost all of modern hacking wouldn't work. But anyway, there'd probably be another hole in it.
Because this is how programming works, right?
Yeah.
If you are in Java, the first one is the primitive data types.
Mm-hmm.
The direct access is character set, and the indirect is object.
Yes, absolutely. It all works at this level, but the weakness is that exactly the same data can be interpreted in any of these ways.
So if a hacker had access to the computer, that means game over, because they don't even have to know anything. They can actually read the addressing and be able to tell what's that. Well,
this is another issue in defense in depth. For example, if you have an encrypted hard drive, the idea is even if they gain access to the machine, they still can't read what they've got because that's the plan. That's the idea. That's why you try to have defense in depth. But this is why this is a huge issue in vulnerability reports. There are a lot of vulnerabilities that only work if you have administrator privileges on a machine. And Microsoft will say, well, we don't care because our security is focused on not letting you get administrator privileges. And there's the big ones that hit the news was Spectre and Meltdown. Spectre and Meltdown are hardware flaws in all modern processors because in order to make the processor faster, it processes more than one instruction at a time with pipelining. So it starts doing instruction number 1, and while it's partway through, it starts doing instruction number 2. So this means if instruction number 1 violates a security rule and will eventually be canceled, part of that instruction has actually been processed before you figure that out. So there are ways to deduce what was happening from the instruction that you're forbidden to execute. And that means you can execute kernel processes without kernel permission, and you can read data that the security measures say you shouldn't see. It violates all these rules, and there's a whole series of attacks coming out of it, but all of them require you to be root locally. So some people say, well, it doesn't matter because you just don't let them get root locally because you have to basically measure the hardware directly. But anyway, it does have a lot of consequences. It means you can steal the password from the trusted element in iPhones and such. So many yeah, that's the point. It's a fundamental weakness in all of our hardware. Anyway, all right, so here's memory protection. this is what you're going to need. Each process should have its own memory, and it should not be able to read or write to the other process's memory. And they all attempt to enforce this with varying degrees of success. So this is process isolation. One process should not interfere with another process. So you have things like virtual memory. Every Windows machine program always believes it's loaded at 400,000 hex. They all think they're at the same location. They aren't, but they work with a virtual memory space where they can only access certain memory locations that are allocated to that process. And the memory allocated to a different process, they cannot access it directly. You have object encapsulation and time multiplexing. Each process gets a different slice of time. These are different systems to somehow prevent one process from trespassing on another process's operation. So real mode is how machines, when they first start are running, this has no process isolation. Any process can write anywhere in RAM. This is the really old model from like the early days of MS-DOS. And this is what happens when a machine first boots up in the real mode, then it loads something and boots into another mode later. That's protected mode. All right. And then there's virtual memory. You have a mapping between process memory and hardware memory. You can swap pages in and out. And if the kernel attempts to access memory, you get a page fault. This is how you can tell when you have a disk problem, or if you're running out of RAM, you will get a lot of page faults because you try to load, like you double click Word to launch Word, but all the RAM is full. So now in order to free up some RAM to load Word, it has to take pages of memory and put them on the hard disk in the swap file to free up some memory to put in Word. And now when you try to go back to that other program that got swapped out, you have to wait while it does a bunch more swapping to put it back in memory. So your machine suddenly gets a lot slower and your disk activity gets a lot bigger as you're constantly writing stuff to disk that really should be in RAM. That's the consequence of having not enough RAM. That's why most people, if their machine is annoying them, well, the number one thing is to clean off the malware. And the number two is to get more RAM. Those are usually the simplest fixes. So the BIOS is code and firmware, which is when you first power on the machine. This runs a power on self-test to see what hardware is there. Do I have a keyboard? Do I have a monitor? Do I have a storage device like a hard drive? If I do, then I will try to boot from a floppy or hard drive or a thumb drive, depending on what I can find. This is write once, read many are things like CDs and DVDs that can be written once and not altered. The Trusted Platform module we've mentioned is the hardware making it possible to meet those military specifications for a trusted computing platform, and it is a cryptographic coprocessor. It is a special chip to hold cryptographic keys so you can have a secret key on the machine that cannot be stolen by any software. There is memory on that chip that is not in the memory space of the processor. The processor can send a signal to the Trusted Platform module saying, decrypt the hard drive using your key, but the processor never sees the key. So no malware or anything on the processor could ever steal the key from that chip. That's the plan. Data execution prevention is putting permissions in RAM. Now, if I am a hacker and I feed in a password that's 1,000 characters long and I trick your machine into trying to execute some of the characters in that password as code, which is how buffer overflows attacks work, it won't work because the data coming in from the user goes onto the stack, and the stack is writable but not executable. So you have this thing called an NX bit in all modern computers. It is possible for the operating system to reserve memory and to specify that it should be non-executable memory. So programs have a protection, and this ends a whole generation of malware. There are ways around it, but that's true of all security measures. Every time you have a security measure, you end the old attackers, and the new attackers find a way through, and then you have to have another security measure, and that's just the way it is. The cops get bigger guns, so the crooks get bigger guns. So the cops get bigger guns. That's how it works. At DEF CON, it's funny. If you propose to talk to DEF CON, they will say right in the original proposal, they say, here, you should give us your talk, and then they say, okay, if your talk is an attack, what's the defense? And if your talk is a defense, what's the attack that punches through it? Everyone knows there is one. Let's hear it. Don't pretend that there isn't one. Whatever you've done, there's a countermeasure, and you might as well address it. All right. ASLR is another big step forward. This means in old machines like Windows XP, you boot the operating system and it just starts at memory 0, puts the operating system low, then you load something like your antivirus loads, then your Microsoft Word loads, then your Internet Explorer. They just stack up in memory like cards, so you can predict what memory location you're in. Modern machines have randomization, so every single process is randomly placed in memory, so you don't know where you are. So this stopped again a whole generation of attacks that relied upon knowing where you are in memory and jumping to that address. Now you can't find an address because you don't know where the process is loaded. So data execution prevention and address-based layout randomization were huge steps forward in security, and they ended a whole generation of attacks from the Windows XP era that were pretty much stopped in the Windows Vista and Windows 7 era. And I think average users could easily tell. Back in the days of Windows 2000 and Windows XP, everybody had Bonsai Buddy bouncing in the corner and porn popping up on the machine, and it was driving you nuts. And Microsoft got so irritated, they had the trustworthy computing memo from Bill Gates saying, we're going to change our entire company policy to be more secure. And they rewrote Windows XP entirely, and they put in these advanced features, and they made all their programming staff read a book called Writing Secure Code and learn how to, because the Microsoft programmers did not know what a buffer overflow was when they wrote Windows XP and all of their versions. The official Microsoft policy was that security is a waste of time. There aren't that many hackers, and all we're trying to achieve is functionality. So normal users trying to do their work can do their work. Wasting your time on some exotic crafted attack is crazy. Let's not worry about that, but they decided to worry about that, and it got a lot better. All right, so I got some cahoots here, 483. Let's try that. There they are. Okay. Okay, I see 6. That's probably it. All right. So, what CPU ring is user mode? Okay, that's 3, the lowest privilege ring. Users can't handle the truth, so the computer lies to them. What is that? What is the dignified term for this situation? That's abstraction. You double click on the picture of a Word document and Word launches. You don't really need to know what actually went into that happening. All you need is the abstracted, simplified view. All right. A communication channel between components. That's the bus, okay? If I launch Microsoft Word, what have I created? It's a process. It is composed of many threads. What's the cryptographic coprocessor? The trusted platform module. Okay. So PC has 3, and Robert has another 3, and FDZZ has another 3. All right. Well, let's take a break till 10:30, I think. I'll stop the recording and start another one then. Have to have some breaks or people will fall asleep even more than necessary. So I'm going to stop the share so it processes. I will reopen this at 10:30 for my remote attendees.